was granted Erasmus Mundus Master Scholarship, which gave me opportunity to double degree in France and Norway together, which I finished in 2 years. Right after that, I joined my studies at University of Amsterdam for continuing my research career as a doctorate student. And I did my studies in artificial intelligence, especially in computer vision. And after finishing my PhD studies, we founded a company with my partner. It's a spin-off of the University of Amsterdam, which develops basically artificial intelligence solutions for big companies like
Германия, она гръчка, мама, там това днес. Так да старс. Насколько се нагора, пек менаш, ле, нагоре.
I don't know if you also hear the sound, but
И нашия глас се слуша.
yeah. Yeah, so we founded this company where we have now 20 people working in it and providing computer vision solutions for tech companies like Samsung or Huawei or these companies, as well as we have our own products. And as my part-time job, I'm still a researcher at the University of Amsterdam, supervising PhD students for their research. And one of my colleagues today, he will be also joining us part-time. He will be helping us with the practical assignment, as well as I'm teaching in artificial intelligence master program. So this is more or less who I am. And I'm as I said, I'm really happy to be here. And it's a little bit strange feeling to be in front of my teachers, trying to share my experience. So I have done a lot of talks and invited speaks in conferences, and also due to the hot topic that we are working at this moment with the company on media as well. We are all around the Dutch televisions, but it always feels awkward when I'm invited to give a talk at my at my high school and also in front of my teachers, because that's where all the knowledge was seated. And I'm happy to see that this collaboration goes beyond, and I always admire also Mr. Özdemir, so that he was also one of my math teachers who was giving extraordinary effort on teaching all of us, not only on school time but out of the school. He was always an inspiring figure for me to do better and do more. And now I see he didn't give up. It was 20 years ago. He's not getting old, obviously. He's just doing more and more. Now I see he's affiliating this group and sharing knowledge, not only sharing knowledge, not only within his student group, but he wants to still share with with all around. So it's really inspiring. And therefore, I'm really happy to be part of it, and I hope I can help. And during my presentation, please, if something is not clear, please let me know. And you can always interrupt me. And I would like it actually more like an interactive session. And I think in 2 minutes we can start, maybe, so that you don't wait too much also. But I can already answer if you have any questions so far. Okay, maybe I can get a permission for sharing my screen so I can share my presentation.
Okay, you can share.
Let me see. Host disable participant screen. So
I'm sorry. Sezer, now you can host.
Checking host. It's still the same message. Host disable the participant screen sharing. So do we know who is the host?
No. You host? No.
I still cannot share my screen. No.
I think that Anna Kara is the host.
I don't think so.
Sezer sen host musun? Şu anda host değil misin?
Değilim hocam.
Niye olmadı ki? Ana Kara host olmuş. Sen ona bir söylesen de hostluğu sana devretse ya. O nasıl host oldu anlamadım.
Karaoğlu'nu direkt oradan şey yapmıştır. Ana, I think by mistake you're made a host. Is it possible to make me host?
I can try, I'm sorry.
Yeah, perfect.
Yes.
Okay.
It's okay, thank you.
Yeah. Can you see my screen?
Yes.
Perfect. It does this time to time. Sorry for this, but let me, yeah. Go to there and share my PowerPoint. Yeah, should be okay. Yes. I guess you can see my screen.
Yes.
But I think I freeze, so there's something weird. Yeah. So today I will be talking about linear regression, and before we dive into the topic, I would like to actually mention why machine learning and why it is sufficient or why it is necessary. And the reason is that as human beings, we are extremely good at some contextual tasks, such as learning new concept or making a guess or trying to make an empathy. But certain tasks, such as decision making from a data, it is a lot more efficient with the help of computers. Just to give an example, that a kid can learn to count just the digits. It takes 3 to 5 years from childhood. But if you have a computer with just a CPU, it will take only 1 day to learn how to recognize a number. And with a GPU, it learned in an hour. So these tasks becomes extremely efficient for the task which has pattern and repeatability. But of course, not everything can be done by machine learning, which I will explain later. But for the task, for instance, another example, if we want to talk about, like a lifetime of a doctor is not sufficient to read an X-ray document that a computer could read in 1 hour. So it's not that if machine learning is in our lives, that it's going to steal our lives. No, it will actually help us to do tasks which will make our life easier. And that's why there is a lot of effort at this moment to involve machine learning in our lives. And during my talks, I usually start with this, that asking, but right now I will not be able to see your hands, that how many of you actually daily use machine learning actively? And most of the time, people are not even aware of how machine learning is involved in our lives. For instance, if you are using your email, yes, you are using artificial intelligence because of the spam filters. Or if you are using a Google search, there's a heavy machine learning algorithms on the background as well for your search to be more proper. Or if you are using Netflix, where you get a recommendation from Netflix, there's also AI. Or Facebook, friends recommendation. Every simple social media or other mobile applications that you're using are actually heavily involved artificial intelligence. So artificial intelligence are actually already in our lives. But not only the task or the Google searches or the Google translates, or for instance, as being an immigrant in Netherlands, one of the main challenges for me, it's a little bit shameful, but 10 years I spent in the Netherlands, but I still cannot speak Dutch. So every time I receive a letter, I immediately use Google Translate and it does a perfect job. And soon this will be already changing rather than a text that you will be hearing and simultaneously making translation. So next generation of, I think I hear some background sound. Don't know if it is.
Somebody is not muted.
Only Anna left, I can mute, but no. I think everybody's muted, but I still hear some sound, which is.
Aslı kızım, dinlesin babanı. Adilciğim, sen artık iyice de yaşlandın, çok yaşlandın. Yaşlandım ben.
Okay, I think better. So not only your Gmail or like your daily task, but AI is also extremely helpful for like environmental issues that we are facing. That AI is already involved in finding renewable energy, or like disaster foreseeing from a disaster scene, like when you have an earthquake or something. So how to involve AI to either early prediction or during the disaster time, that how to avoid more damages, or help to avoid climate change, agricultural support, air and water cleaning. So AI is actually taking a lot of important role in our daily lives, how to actually make things better. But why this is happening now? Why it was not 20 years ago or 30 years ago? Fundamentally, there are, of course, multiple reasons that algorithmic development side as well. But the main reasons are two. One is the exponential growth of computing power. 10 years ago, 20 years ago, with the devices like GPUs that we are having at this moment, was not feasible. At this moment, we are one step closer to a GPU device, which is actually similar capacity of the human brain. So everybody with $1,000 will be able to buy in 30s maybe a powerful computer, which is more or less a human brain capacity. And at this moment, maybe we are in the as you can see from the graph, that is more or less in between mouse brain and human brain, and we can still have a lot more than what we have done in 10 years ago. So this, because all these AI algorithms, especially the current ones, deep neural networks, it requires a lot of processing power, and that's therefore why we couldn't actually have these advances in 10-20 years. And also another reason is data. Like 10-20 years ago, our mobile, we didn't have these mobile phones where you're connected all the time while you're taking selfies or sharing images or being in social media. You're constantly being watched. So every single moment that we are actually acquiring this data to the owners. For instance, like in Facebook, every second that there are 41,000 posts, or 350 gigabyte of data uploaded, or on YouTube, like every hour or every minute, the 72 hours of video are uploaded. So this is a huge content, and that's why this content is data, and this data is gold. Because if you consider, hypothetically speaking, of course, there's a joke in it as well. The big difference between the gold and oil, they are reducing, they're declining, and the data is only increasing. But that's not the only reason why data is valuable, because data carries a lot of information about yourself, and it allows to make predictions for the algorithms. Like, I don't know if you have seen also in this in 2016 elections, where Cambridge media was involved in the Analytica was involved in the manipulation of the election, where they get user behavior from the data, and actually for those ones who thinks they are in between voting to one party or another one, they keep sending posts which they will change their mind. So they can actually have the power to influence people. Or how many times you just talk about something on your mobile phone, and then while you're searching on Google on something, you immediately see the advertisement. So data is going to make you consume more and more. And this is called also content personalization. So you give your consent to those WhatsApp, and that's why all these companies are asking your consent to get all the data in your mobile phone, because that gives who you are. And if they know who you are, then they can sell you more products, or they can involve you on other things. So that's the whole game about the data. And more the data that you have in the governmental level or country level, you have more information about the society, and how to steer them, how to manipulate them, how to also in between countries, how to be more powerful because of the data. So the next generation of the wars or things are basically on the digital environment. It will not be any more physical, but it will be on the digital world. How do we learn any information from data? So this is a rough sketch, and this is called a supervised learning, where you have labeled data, and you have, let's say, big amount of data that you want to extract information. So you label it, you give information with the supervised data. That's the most important thing. You tell this is apple, this is banana, this is, so you annotate it. And then once you annotate this information, label information, the supervised part of it tries to extract meaningful patterns. How I can use this label information either to group them or predict them or classify them and create some algorithms. And using this algorithm, once you build it, next time you just need to put the data and it gives you the output. So you don't need to do this training all the time. You just define it one time, and the algorithm receives input raw data and then outputs a result. And there are, of course, like many ways to do this learning, data from learning, and all algorithms are categorized under machine learning. And here I try to label a couple of them, like supervised, unsupervised, reinforcement, but there are many more also, semi-supervised, and many other. But since the concept of these tutorials will be focusing on these three, I limited the presentation and the linear regression, K-means, and today I will be mainly talking about the linear regression. Simple regression algorithm is a mathematical equation that describes the relationship between your variables. Imagine you have one input data and you want to predict the output. So a regression algorithm is trying to learn this relation, and that simple regression model actually includes two variables. One is dependent and the other one is the independent. So independent variable that you will, we will come back to that later, that you given an independent variable, you try to predict the dependent. And it sounds like a little bit of a probability, but it's a little bit different. So, and not a simple regression, but simple linear regression. And I think it already rings the bell that you try to estimate the linear relation between the dependent and independent variable. And as you know, a linear equation can be defined as this. And the beta here is called a slope, and the alpha term is here is the intercept or constant term. An independent variable here is x, and the dependent variable is y. And actually, when you have data, we basically try to find this equation so that next time when you have a new data, you just put the dependent variable and predict what the output will be, as in this example. So if we plot this linear equation, you will see given an x 10 and y 100, x0 10, then this equation, how do we get this equation? And you can see the change in y and change in x actually defines part of this equation. So as I said, so how do we get this equation given the data? Here is 2. Simply, you can just take x2 minus x1 divided by y2 minus y1. But it's not always you have sample data. So once you have hundreds, thousands of data, how do you handle it? Of course, there are many other ways to do it with covariance matrices and also gradient descent and so on and so. But one of the easiest way that's considered as using least squares estimation, where you try to basically minimize the this is the mean value, and this is there is a bit of typo here. So this should be the prediction, and which should be the hat, and this is the actual value. So the difference, the square difference of this one here, you can consider it should be basically close to 0, and that will define your fitting regression is good or not. And basically what you want to achieve is minimize the SSE equation. And simply if you, how you do that is, as you all know, that we take the first derivative and they will give the optimal solution. And if you equalize it to 0, that will give the optimal solution for this equation. And once I didn't go in all details of the derivation of this equation, but once you derive this, it turns out that the slope is equal to xy sum and minus sum multiplied by x y sum, and then x square sum minus the sum x square. And then the intercept is given by this equation. And the part is that this intercept point or this line must always pass to the mean of the x values and to the mean of the y values and to the mean of the x values. And if we want to give an example here, so what does it mean? So why do we need this linear regression? So just giving an example of a study case, like this is hours studied by a student, and these are the marks that they received. So if they study 1 hour, they get 16. If they study 4 hours, they get 22. So you try to find the relation between how many hours if I study and what will be my score. Of course, this is an ideal case. It depends how efficiently you work or whether you have a background knowledge and things. But let's forget about all those things. And we believe there is a direct correlation between the hours studied and the results that you get from your exam. So if you think about it, if you do the scatter plot, this is how it looks like. So you can see a clear regression line can define this problem properly. So what you need to do is basically find this best fitting line here. And using this equation, how do we find it? So if I take the slope information beta, that you sum up all the x values and you continue all for y, x, y, and x squared, and then this is what you get. So basically beta values boils down to 245. And here you can see because for the other equation, that alpha, the intercept, is equal to the mean of the y and minus beta mean x. So if you take the whole sum of the x and all sum of the y and take the average of it with the number of elements, so then you get the mean, and then you can basically put it in the equation. Then it goes down to the fact that this is 2.71. 12.71. So our equation is y is equal to 12.71 plus 245. So this is just from a given data how your regression line looks like. And this regression line, why it is useful? Because next time when you want to make a prediction of how or the relation between what will be my score, simply what you need to do is, okay, if I study 10 hours, what will be my score? So the score will be on this line. Of course, in reality, it can lie anywhere in this one, but we approximate the result, we predict. So that's what the algorithm does. It makes a prediction for you. So using the previous knowledge of data, you try to make a new prediction or assumptions. Or if it is 15, that's what you get a mark of 50. And a regression looks like this. So this is red points are your data, and basically this is the regression line, and this is your equation, and this line is the mean of the y values. And from these dots to the regression line, these are called residuals. The C's are called as residuals, which means the prediction error. So this is what you predict, and this is what your actual value, and that is becoming the here. This is the prediction minus the actual values. So that's becoming your residual, which is your prediction error. And what you do here is I cannot see from here, but I will try to. Yeah. So here what you see is the total regression error is basically the one, which is actually, and how far it is from the mean. So this is considered as A. So if you look at the regression line, distance to the regression line to, sorry, the actual values to the mean value, the difference is considered as A, which is the total error. And also when you look at the prediction minus the mean, which is considered as B, and this is the distance from the regression line to naive mean. So how you calculate the total error is basically using the A square here is equal to B square plus C square. And here what you want to do with the beta, what we were trying to do is to minimize the C square. And there is a term called R squared, or correlation coefficient squared, which means that how good your fitting line describes your data. So that gives an indication once you get the R square value. If it is high or low, it can give you an indication, okay, your problem can be described with a linear regression. And this is mostly used also in a t-test, like statistical tests as well. But in this context, given a data, how well I can fit a regression line. So that will give you an indication. And R square is actually the variance explained by the model and divided by the total variance. If you look at the equations, these are actually, it refers actually to the variance. And here, what does R high, R low means? So that means your data is nicely fitted on a regression line if R square is high. And if it's scattered around a regression line, but there are some kind of considerable errors, your R square will be low. But it doesn't mean that R square high is always good. For instance, in this problem, if you calculate R squared, for this one, it will be around 95, 98. But this is a significantly biased prediction. So your data is quite important that it actually is a good fit for a linear regression problem. Because if you are considering here, if you check the residuals, that all your residuals here will be positive, and here in the negative direction, or here in the positive. So all predictions will be one direction here. All the residuals will be in one direction. So it will not be varying over two dimensions. So this is called a biased prediction, and this is not what you want. And obviously this solution produces high R-score, but it's not good. So what you need to do is don't just believe in the R-score, but check the residual plots. How does the data look and the fitting line looks? So that will give more indication if your problem is solvable with a linear, or if your problem is a linearly superposable, or if there's a linear correlation between the dependent and the independent variable. Such as in this example. So there is a direct or linear relation here, and when you plot the residuals, you can see it is a normal distribution over the regression line. So you can clearly see it. And also the second one is the variance of the y at every value of x is the same. So it homogeneously have a variance, such as in this example, you see that the y value and over the regression line will be, the residuals will be scattering not in a normal distribution. So it will be that having a low variance here and high variance here, but here it's equally. So you should have a constant variance over the residuals, as well as I tried to explain in the example where the R-score was high, but the problem was not really a linear solution, that you should have your the predictions or your data over your regression line should have a normal distribution. Otherwise, it will be heavily biased towards a certain predictions. And also observation independence. So the data must be independent. So it should be the independent variable should be really independent. Otherwise, it will have some kind of, again, bias towards here. So above, you can see the residuals here are higher than the here. So residual distribution should be, again, somewhere in the mean distribution. But not all problems that we will face are considered as a single dependent variable. So there are multiple linear regression, which is most commonly used. So it has more than one independent variable which describes the dependent variable. Here is for instance, a linear regression is described with only one independent variable, whereas in multiple, so you have to use all these predictors and then use y. And another reason why R-score can be dangerous to consider all the time is because once you start to increase this number of predictors, your R will be heavily biased towards it. So you can change the R-score with respect to the added predictors. An example to this problem can be considered as, let's say you have a cognition problem, and there are some factors, but you don't know which one affects the most. What you want to do is to understand which factors is actually causing the cognition problem in elderly people. So the assumptions are older men have lower vitamin D and older men have poorer cognition. So are they correlated, or is it related with the age? Because there's two factors here I can see, older and poor vitamin D. So once you try to define your problem with the DSST score, which is basically the cognition capability, that it's exactly the same as a simple linear regression, but with intercept plus slope 1 and slope 2, which is a definition of the vitamin D and the age factor. Of course, now we cannot plot this in a 2-dimension, but this needs to be in a 3-dimensional space. And here you can already see some correlation between the age and the DSST score. It is negatively correlated. So your DSST score high when you're in a younger age, and it gets lower and lower. And with vitamin D, you can see there is not much correlation. So this plot already tells you that there is a high factor of effect of DSST score with aging. And yeah, so basically here, instead of plotting lines, you basically need to plot planes. So the presentation is for a regression, linear regression is finishing here. And my colleague, as I explained, he will try to give some practical session on how this data can be collected and how this data can be used with existing tools. So what I have been trying to explain the mathematical formulations, but I have to be honest. So these courses that we take with linear algebra and things, you don't usually use this while you're coding or while you're using the tools, because there are already available tools which already does most of the problem solving for you, so that you just define your algorithm with how you want it to be fitted. Is the parabolic, is it the linear, or is it the non-linear? Then the algorithms are already computing those things. So that's why you don't need to worry about the computational part of it, or you don't need to do this with hands. And also sometimes, like I mentioned, while you're trying to find the solving this beta and alpha problem, of course, gradient descent can be a decent solution when your data is not a simple linear regression, but multivariate, where you have thousands of dimensions to your problem or predictors, where it will become extremely complex to do the matrix decomposition and also comply the rules of the positivity and all those things, and also taking the inverse of those matrices. So it will be extremely computationally expensive. So that's why sometimes you need to do the iterative approach like gradient descent, or you need to find other fitting or least square kind of solutions. Of course, least squares will be more problematic when you have multiple dimensions. But what I'm trying to say is, of course, it is good to know the underlying the math, and everything is like basically ruled by math on how you're solving these things. But for the ease of the use for the students that you're going to explain, or for yourself, there are already available tools which perfectly does this job. And I will leave the stage to my colleague now. And if you have any questions, please let me know.
Okay, thank you, Sezer. Hello, everyone. Good evening. My name is Partha. I am a PhD student at the University of Amsterdam. I am from India. I did my bachelor's in computer science, and then came to the Netherlands for the master's in artificial intelligence, where I met Sezer, and we worked on some projects together, and I kind of stuck around. And I started my PhD, and he is my supervisor for the PhD project also. And yeah, it's really nice to be able to explain this, and yeah, it's also quite humbling. Okay, so without further ado, my part, like Sezer explained, the theoretical part behind the linear regression, and so I would like to give some visual intuition about how you can use linear regression to solve a problem in the real world, or your day-to-day work also, maybe. If during the presentation, if you have any questions, please let me know, and I'll be happy to address it. Okay. I don't have access to sharing the screen.
Can you try now?
Yes. Okay. Can you all see my screen?
Yes.
Okay, so this is Orange. This is a Python-based tool for like data mining, so you can like visually analyze the data, and it also comes with a lot of models that you can use to train. So one of the models is linear regression, which we are going to look into it today. So before we begin, I think it's also nice to have an understanding of the data. So for this data, we're going to use the high school data, from Portuguese high school, 2 of them. So this data set already comes with a collection of 395 students that along with various attributes. So if you can see on my screen, you have each of the rows are the attributes of different students, and each of the columns are the different attributes. So for each of the students, you can have things like the guardian, the age, the address, the family size, which stands for more than 3 people, less than 3 people, the present status of the parents, the mother's education and father's education, and other things. So in total, we have like 33 attributes, out of which the last 3 are the grades. So G1 is the first grade, G2 is the second period grade, and G3 is the final grade of the year. So for this problem, the idea is to take all the features up till G2 and try to predict what the final score of the student will be given all this information. So one of the things that we would like to see is, like, at the outset, like, which would make more sense to predict the final score. So by just thinking, like, with our knowledge, by teaching from teaching or learning through school, and by intuition we can say that G1 and G2 might be very correlated to G3, because if a student is performing really well on the first and second exam, they might also get very good score on the third or the final exam. While this is almost always certain, but there might also be some outlier cases that might not be that true. Also, similarly, you can have, like, the correlation between the absences and the final grade. So if a student is absent too many times, their grade might go down, as you can see here, while if they're always attending all the classes, their grades might also go up. So one way of checking that can be through the data analysis tool. So for that, what we do is we go open the program and go into the data tab on the left, and then we drag in a file node. What this does is basically read in any of your file, which is like comma-separated database files. So you can double click on the widget that will give you this dialog, and then you can open the file picker. So for this, I have them saved in this file called studentreplace.csv. I love that, and for that, and it gives you an overview of all the features that you have in the file. So as we said, there are 33 features in the file, and each of their name, the column name, are given along with the values and the type. So there are 2 types of variables. One is the categorical and another is the numerical. The categorical is basically saying you have a category assigned to that. So because the data set is collected from two schools, it has the entire set of the school contains 2 values, so GP and MS. So and for each student, it can be only one of these values. It can be either from GP or MS. Similarly, for the gender, you have the male, you have the female, you have the address, which R stands for rural, U stands for urban, and similarly family size, etc. So once you have the data imported, there's also the part about setting which of these variables for your equation. So like if you think back into the linear regression, you have like the dependent variable and the independent variable. So for us,
okay, sorry to interrupt, but I don't think I can see what's going on your screen.
Oh, okay. Let's see. Okay, sorry. Now?
Yes.
Yeah. Okay. Sorry.
You can start. Yeah, with this part we didn't see, so maybe you can start again.
Yeah. Yeah. So once that dialog comes up, you select the file, and sorry. For me, it's selected under student replace.csv. Once you load up the file, you have an overview of all the files all the attributes in the file. And you can see like the name of the school, the age, the address, and so on and so forth. And you can also see like there are two types of category for each variable. It can be categorical or numeric, which basically says a numeric would be like age. You can have like a whole number or a floating decimal number representing the feature. And categorical can be part of this set. So if we go back to the original data set, we can see like this categorical value of school, which is GP. And if you go down, it changes to a different school, which is MS. Similarly, for the gender, you have like the male and the female. So these are not numerical values, but specific to 2 points of category. The other part is the role of the variable, which is basically is it a feature or a target? So thinking back to the presentation, so the feature is basically saying it is an independent variable which should be taken into consideration to predict the target. So if you think of it in a two-dimensional case, the feature is the X value and the target is the dependent value, which is the Y. So for some word cases, you can set multiple target values. So that will be different cases, for example, a neural network and stuff. But for our cases, linear regression, we have just one target value. So we set the final grade as the target value because that is the dependent variable that we want to predict. Okay, so once it's done, we can move to the main file. So once you have imported everything, it's always nice to check that everything is imported correctly. So you can go into drag off a node from there and click the data table. And if you double click on the data table, you'll have this window show up where you can see all the features arranged. The target of the dependent variable is put in front and it gives a different color, and all the features are set in as they are imported. One thing to note is like the small lines that you can see with the numeric features is basically telling how the magnitude of the variable compared to the maximum value in that feature. So for example, the grade is the maximum is 20, so you can see the 19 is quite a large magnitude, so you have a larger bar for it. It's something nice to have when you want to judge something at a glance. So, oh, sorry. Yes. So once you have that checked, you can also look into the correlations between the various variables. So for that, you can drag a node from the data table and plot the data. So one of the data we can see is like we set like the y-axis to the final grade and the other axis, x-axis to the attendance. Absences. So if you can see in the graph, you can see like the color of the value kind of shows what kind of what the grade value was. So yellow means higher grade and blue means lower grade. So you can see
again,
like,
we cannot see.
oh, sorry. Okay, yeah. So if you see the graph, it shows the value of each of the students and against the number of absent days they've taken. So if you see like some students who has not taken any accent, they're mostly in the higher performance that can be seen from like the yellow dots compared to like students that have taken lots of accents. They're generally on the lower end of the grade. But again, this assumption this assumption is taking into account that other variables are constant and only the absences are changing for each of the students. So although it might seem more logical here, it might not be the complete explanation of the entire situation, because you can also see this student who doesn't perform that well, but they are not absent on any of the days. Similarly, you can also look into a categorical value where higher, which basically says if the student wants to go for a higher education. So you can see like students that don't want to go for a higher education generally performs less compared to the students that perform that want to go for a higher education. But again, here you can see like this student, even though they don't want to go for a higher education, they're performing in the higher brackets. So you can see like some of them are highly correlated, some of the values are highly correlated, while some of them are not. So so we have to kind of keep that in mind while designing our algorithm and like an experiment to see what the most important variables are. Okay, so so with that out of the way, the way we first go through preparing the data for the algorithm is first we try to pre-process them. So for that, we drag off a line from the file system and we search for the pre-process node. This is because not all the data is always clean. So you can have like a set of data that's quite noisy. So you can have like, for example, in this data table, you can have like the gender, which is not a number, or a school, which is not a number, or you could have like values that are missing, like maybe this gender value, age value is missing, or maybe some of the columns that doesn't exist. So in order to make sure that those things are not those things does not get fed into the algorithm, it is important that you remove those data set or pre-process them. So one of the things that we pre-process is by using the impute missing values, which basically says if there are missing values in a column, take the average of the column and then replace that in the missing value place. And the second one is continuous discrete variables, which basically says if you have labels like the gender or like the school or like the family size, try to make them into a categorical, numerical feature. How it does that is basically sets, like divides up the feature into more sub features. So basically, if you have like, for example, school, you have two options for school. It could be the MS or the GP. So how you can change it into numeric, you can create like two columns that says school is for MS and school is GP, and give a 1 to this for the students that are from the GP school and 0 for the students that are not from the MS school, and vice versa. So we can do this with the pre-processing, and to give you a visual understanding of how that looks, we can see how the data looks after the pre-processing. So if we double click this, we can see that if you remember what I was saying, like the GP has GP, the school has GP and MS. So for students that are belonging to the school GP, you have 1 in the GP column, but 0 here. And if you go down, you see like the students that belong to MS have 1 in the MS column and 0 in the GP. So what this does is basically take the entire feature and changes all the features into a numerical value. So so it's like you can perform matrix operations directly on them. Similarly for address, the family size, and the parent status, and other mother's jobs and father's jobs, etc. One thing to note is like after you do this pre-processing, the feature count increases to 58, whereas previously it was just 32 features. So if you compare this and this, you can see like the 32 features has been expanded to 58 features because we broke up each of these features into multiple columns. Okay, so once you have the pre-processing done, we are one step closer to using the algorithm. So, but before that, we also want the algorithm to not learn a sequential set of data. So basically, what we do is ask the algorithm to randomize the data. So there is no bias. So because if you see the setup of the information that we feed in, we see that the first few are always GP and the second and last few are always MS. So what the algorithm can do is, if it is not randomized, it will basically memorize that, okay, the first few are GP, so maybe GP is scoring high and then MS is scoring low. And depending on the distribution of the data, it can also reduce. It can also have a low error rate, but still not be correct when you're testing in the real world. So for that, we randomize the data. Once we randomize the data, we also want to split the data into different sets. So because what an algorithm does is basically takes all the data point and fits the best fitting plane. So if your data, if what you're going to test on the data is already in the training set, it will be already in the fitted plane. So the result when you're testing out in the real world might not be representative by that training set. To give a more common example is like students taking an exam, studying for an exam. If they're given the questions that are going to appear in the exam, they might have a high score in the exam itself, but once they are done with school and they go to the real world and they have to solve a problem that has similar questions, they won't know how to solve the questions because they didn't see it and they didn't actually learn how to solve that exact same problem, even though they have a high score. So in order to prevent this, what we do is like we split the data into a train set and a testing set and a validation set and a testing set. We train the algorithm with only the training set so that the algorithm does not memorize anything that is in the whole held out testing set. And then we check the performance of the algorithm on the validation set. And depending on the performance of the validation set, we might want to tweak some of the parameters in the algorithm and then test again. And once we are satisfied with the validation performance, we check it finally in the real world test set, which was never seen by the algorithm. And in theory, if the algorithm performs well on the test set, that means the algorithm has learned how to solve the problem. So for this, Orange does not come with directly preparing a test and train validation split. So we have to do it in 2 steps. So what we do is after the randomizer, we select a data sampler, which basically returns two data points. So if you double click on this line, it basically says what is being sent. So the first is the data sample, which is the first part, and the remaining data, which is the second part. And in order to define this split of the data, you can double click on the data sampler and say how much of the data proportion do you want to split into. So for this, we will go for a 80-20 split. So 80% of the data will be our training set and 20% will be our validation and test set. We do that and we do a sample. So here you can see like out of 395, 80% is 316 and 79 is the remaining 20%. So we can visualize this data here. So these are all the randomized data. You have like 316 samples. This will be our test set. So we can rename that by clicking on this and pressing F2. We can say this is our train set. And then we can also drag out another sample, which is basically we can similarly name test set, test and val. Set. And one thing to keep in mind is we are still seeing that data sample is returning data here. So we have to make sure that is changed. So remaining data is trained in sent to data. We set that up and we see this is the other set, other remaining set. Now, in order to split the remaining test and validation set into a test and separate validation set, we pass it through another data sampler where we set the proportion to 50%. So 50% of the 20%. So basically you have like 10% of the full data. You can sample that and make sure that the data being sent is the remaining data, not the training set. And then you can check for the data table. You can see the first one is 40 samples, and the second one is once you change that is this remaining 39 of the data sample. So in this way you can set this to your validation set and the other one to your test set. Okay, so once that is done, we can then move on to making a training the regressor itself. So for that, what we can do is select a model from the available models. So we want to train a linear regressor. So we drag in there. So if you mouse over, it says what the inputs are. So you can see like the input, it needs a data. So the data that you want to train the model on, and the preprocessor, basically, if you don't preprocess the data, it can also take the preprocessor and process it. For us, we are already preprocessing the data, so we don't need that. So for this linear regression, we can connect this data. So for the train set, which is data sample to data, we connect this one, make sure the data sample is pointing to the data. We click OK, and that is training a linear regression here. But how do you check the performance of the linear regression, whether it's actually working properly? So for that, you can go into evaluation, go into test and score. And for this, if you mouse over, it shows you the input, that is the data, the test data, learner, and preprocessing. Because we are already preprocessing all the data, we don't really need to connect a preprocessor. We can just connect the data, the test data, and the learner. So for us, the learner is the linear regression. The data is the original sample data, and the test data that we're going to select is this test data. So just to make sure that the test data is not the validation data, we connect the remaining data from the second data sampler as the test data. And once that is done, we can double click and see that our performance is like this. So you can check on the train data. So the train data, you can see like if you check the performance, our linear regression performs well. So you have like an MSE of 15 and the RMSE and the mean absolute error and the R2 coefficient. Then if you check on the test data, you see like the MSE actually goes up. This is expected because this means that the data distribution is separable, and the model is not able to cheat. So most often what happens is like the model that you train performs well on the trained data because it's seeing all the examples, so it can memorize it. But then on the test data, the performance drops a bit. But for example, for classification and other things, you can check the accuracy if like 80% or 90%, but that depends on the type of model that you're training. So one way to check how to improve the model is to check what are the most important coefficients or the variables that contribute to getting the proper grade prediction. So for that, what we can do is visualize the coefficient that's learned by the linear regression, and for that we can drag off a node and show it in a data table. And if we click that, we can see like it has a coefficient where the intercept is minus 0.75, and each of the independent variable has a coefficient. So if you think back about the presentation, it's also the values of the x in the multivariate regression. To think about the coefficients that we check with the scatter plot, the higher education and the absences, where we concluded that absences is directly is an important indicator. We can see like if we go here, so if you see like the absences, it's positively correlated for this, and we can also see like the higher yes is also positive. So if someone wants to go for a higher education, their mean average grade is generally higher compared to no. But we also see that more correlations are to this assigned to school GP than school MS, and also like the female students and the male students. And one thing we can notice already from here is that these coefficients might be a bit biased to that school. And in order to explain that, we can look back at the data set that we had. And if we go and analyze the number of entries that these have and do a simple bar chart, we can see like the number of GP records are much more higher than MS. Similarly, for the male and female students, the data set is kind of biased. So these independent variable might not always be a good indicator and might act as noise for your algorithm for the prediction. So one way to fix this or improve the performance is to basically remove these independent variables which doesn't contribute much. So for example, like this type of school that they're going to does not really correlate to their grade or their gender or their age, or even maybe their dress, maybe rural and urban, that can be related to the family size, or the father and mother job, those kind of stuff. So one thing that we can do is basically remove these attributes. And for that, what we can have is we can have something like this, which I already did. I removed some of the attributes and reduced it to only these attributes. And if we check with that value, for that, what we can do is basically load up that CSV file, and you can see you have an overview, and we set the G3 as the target and apply, and we can see the performance actually increase from 35 to 23. On the test also, you can see like the 18 goes down to 17. And if you check on the test, all of the performance goes up. So one thing to keep in mind is even though linear regression can appear to be a black box, or any algorithm in AI that can appear to be a black box that simply looks like it works if you throw enough data, there is still some need for understanding of what the data is, what each of the variables of the data actually contribute. So for example, like here, the unbiasedness of the gender or the type of school kind of reduced the performance by quite a lot, from 35 to 28. So 23. So that's like 12 points of increase. So you still have to like explore these through tools like the scatter plots and the coefficient exploration of the learned algorithm. So that is very important to in order to work with linear regression, and these kind of tools like the orange, they help make it faster, because they already have these tools inbuilt, and you can just drag and drop and connect and make your own system. Okay, so finally we have the trained model, which actually works nicely now, and then we can now see how to predict. So what if once you have trained your data, what if there's a new student that you want to predict their final grade from? So for that, what you can do is basically create a prediction from that. So for that, you take a prediction widget from here, and again, if you mouse over, what you can see is like it needs the data. So the data that you need to predict, and the predictor, which is basically the model that you have trained. So we already have the model trained, so we'll connect this here. And for the data, I will import a new file, which will load a new file called predictions.csv. In the predictions, if I show you here, so these are just 3 samples that I made randomly from the main training set that was excluded from the training set. And for this, these have all the attributes that was trained. It was trained with. Just one. So we import this into the main orange file. Now, once we load this, we have to make sure that because we didn't use these attributes to train this model, so we can just make sure these are skipped. So we drop the first 3, and also we skip the final one, because yeah, we want to predict G3. So there's no point in feeding that data. So we make sure we skip these. So it starts from the address, and in order to verify, you can double click your main file to see if they're corresponding. And I can already see I was going to make a mistake, is that address is also not included in the data. So we go back and skip this. So now we see we start from family size, and we go down to all of this. And we go down to all of this. Oh, also the G2 is skipped. So there. So we apply, and we close that, and then we connect this. And we can already see if we double click on it, the linear regressor says, okay, the first student should get like 10 points. The second student should get 9 points, and the final student should get 12 points. And if we go back to our prediction file, we can see is the first student is got like 15 points. So 10, 15, 6 points. Okay, still close by, and 9 points still close by. So it is able to predict. So but it's not on the point. But then again, the regressor only had like 300 samples. So if you also like we just pruned one time of the uncorrelated value. So if we look into more detail, we tweak the small numbers and see exactly what we are fine-tuning more. And then it might get even better and might even get closer to the prediction. And also, again, if you take more data, that noise can also be factored out because you're fitting a larger, more flexible plane to it. Okay, so yeah, in this way we can train a simple regressor very quickly. I think in about 30 minutes we went from taking a full set of data, analyzing it, and pruning the data and training a regression that can do predictions. I hope you find it interesting and you give it a try. Thank you. If you have any questions, please feel free to ask them.
Thanks a lot, Partha.
Thank
Thanks
you,
a lot.
Sezer and Partha. Thank you.
Thank you. Thank you.
Sezer, programın devamını istersen anlatabilirsin. Sonra kapatırız.
Efendim hocam?
Bir dahaki programı kısaca anlatabilirsen hani kapatabiliriz ondan sonra.
Tamam hocam. Yeah, so thanks for joining us today. I hope that we were a little bit giving instructions about touching just a little bit of the surface of what machine learning is actually doing and and how this data can be useful. And today we touch upon a little bit of a supervised, and that requires a lot of manual annotation because, as Partha explained, you need to have a training set where you define these labels. This is true, this is false, this is number. So you have to, and there is not always this amount of data. So there is also a method called in machine learning unsupervised learning, which is mainly considered as clustering algorithms that you try to find the correlation between your samples. And in the coming sessions that we will be touching upon these topics, which is called k-nearest neighbors or k-means. So in the next tutorials, basically we will try to explain when you don't have enough label data, that how you can actually extract some kind of semantic information to make it useful. And we hope to see you also on those tutorials. And thanks for listening.
Thank you.
Thank you, Sezer.
Yeah, thanks a lot. And if you don't have any questions, then I think this session can be over and we can wrap it up. And have a good night all.
Thank you. See you again.
Thank you.
Thank you.
Thank you, dear partners. See you again.
Thank you.
Thank you.
Bye.
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 Thank you.
Thank you.
Thank you.